The next question that I want us to take a look at is this question here, where they tell us, given the following diagram, and you can see there you have a hydrochloric acid molecule bonded to another hydrochloric acid molecule. Then they ask us a couple of questions. They ask us, name the molecule and circle it on the diagram, label the interatomic force, and then also label the intermolecular force. So, if we take a look then, we know that we have hydrochloric acid, and this hydrochloric acid is bonded through covalent bonding. And that's one little hydrochloric acid molecule. And we can draw the second one. So let's just take a look at each individual molecule first. So firstly, we know that that is our bonding pair, and we know that we're dealing with a covalent bond. Okay? What's very important to understand also is that we know that we're dealing with a polar molecule, with the chlorine having electronegativity of 3, the hydrogen having electronegativity of 2.1. So that means the chlorine side of the molecule will be slightly negative, and the hydrogen side of the molecule will be slightly positive. And this is just because of the fact that the chlorine has a higher electronegativity. So it's pulling harder on the shared pair, pulling it towards it, and therefore it spends a little bit more time around the chlorine. Now, when these two molecules bond to each other, we know that the bond between them, that intermolecular force between them, is going to be a dipole force. Okay, so it's very important for us to be able to distinguish what these forces are and how they actually bond to each other. Okay, the next question that I want us to take a look at then, they give us a little table, and I'm just going to put it down there so that we can see the question. So given the following molecules and solutions, so they give us a whole list of molecules and solutions, and then they tell us to complete the table. Okay, so they want us to take a look at each one of these molecules individually, and they then want us to be able to tell them which type of intermolecular force would be between each molecule. Okay, so the first one that we're going to take a look at then is hydrochloric acid, okay, which we did in the previous one. We already know that hydrochloric acid is a polar molecule, and therefore we know that it's going to be making use of dipole forces. Okay, the next one then they give us is carbon dioxide. So we know that carbon dioxide looks like that, and we know that the shared pair spends more time around the oxygen because the oxygen has a higher electronegativity. The oxygen's electronegativity is 3.5, whereas the carbon is only 2.5, making the oxygen sides of this molecule slightly negative, meaning it's a non-polar molecule. So for a non-polar molecule to bond to another non-polar molecule, we know we're going to be dealing with London forces. Okay, the next one they give us then is iodine. So it is a diatomic substance or diatomic molecule, okay? And our rule tells us that all diatomic molecules are non-polar molecules. So because it's also a non-polar bonded to a non-polar, we know we're also going to be dealing with London forces. Next we have water. Okay, so we have H2O, and like we saw in the previous lesson, that when we're dealing with water, we know that the oxygen side is slightly negative and we know that the hydrogen side is slightly positive, making this a polar molecule. And because it's a polar molecule, and because it's got a hydrogen bonded to a highly electronegative oxygen atom, we know that in this case we're going to be dealing with hydrogen bonds. Okay. The next one then, potassium, but they tell us that it's Ki aqua. And in grade 10 you learnt about that, aqua. Aqua means dissolved in water. Potassium iodide is a ionic substance, and water, like we saw here, is a polar substance. So we've got an ionic substance dissolved in a polar substance, and therefore we know we're dealing with ion dipole forces. Then they give us ammonia. We also did this in a previous one. So we have ammonia, and we know that ammonia actually looks like this. It's a nitrogen atom standing on its three little hydrogen atoms with that lone pair at the top. And we also then in the previous lesson saw that that means the nitrogen side is slightly negative, but also that the hydrogen side is slightly positive. And then we also have the fact that we have a hydrogen bonded to a highly electronegative nitrogen atom. So that means it's following the Knopf syndrome, and we know that we're going to be dealing with hydrogen bonds. Okay, the next one then, the same as the potassium iodide. So along with this one, we also have sodium chloride, aqua. So sodium chloride, same thing. Sodium chloride is ionic substance, and it's aqua, meaning in water. So we know we're dealing with an ion dipole substance. Okay. Then we have hydrofluoric acid. So HF, and little atom or little molecule looks like that. Again, we know that the fluorine side will be slightly negative because fluorine has an electronegativity of 4, hydrogen only has an electronegativity of 2.1, making it a polar covalent bond. But then also it's a polar molecule because there's a definite opposite positive and negative side, and it's following the Knopf syndrome, hydrogen bonded to a highly electronegative fluorine, so that means we're dealing with hydrogen bonds. Okay. Next we then have magnesium chloride in carbon tetrachloride. Okay, so when we're dealing with magnesium chloride in our CCl4, or carbon tetrachloride, then we've got a couple of things we have to take a look at. Firstly, magnesium chloride is ionic because it's a that rule of ours that tells us any group 1 or group 2 element bonded to a group 7 element is always ionic substance. But carbon tetrachloride is a little bit more difficult because CCl4 looks like this, and we know that chlorine has a higher electronegativity than the carbon, and because it's one of our symmetrical shapes or ideal shapes, we know that the entire outside of this molecule will become slightly negative. Chlorine electronegativity of 3, carbon only 2.5, meaning all the shared electrons in each one of these bonds will rather spend time around the chlorine than it will around the carbon, making the outside slightly negative. The also very important part here is then we have an ionic substance in a non-polar substance. So with this entire solution where we have ionic substance dissolved in a non-polar substance, we know that we're going to be dealing with ion induced dipole forces. Okay. Next then we have two molecules that has the no, sorry, not two, just one. Nitrogen oxide, which is a polar molecule, mainly because it's linear and the electronegativity difference of nitrogen and oxygen is different. Nitrogen 3, oxygen 3.5. So oxygen would be slightly negative, nitrogen slightly positive. So it's polar with polar, and in this case we have dipole forces. Okay. Next then we have argon, so the same as the one we did with krypton. So argon bonding to other argons, it's a non-polar substance bonding to a non-polar substance, so London forces. Okay. Then we get silicon oxide. Okay. Now I'll never ask you to do silicon oxide, because silicon oxide, silicon is one of those elements that we don't do anymore really that much, because of the fact that you guys don't really do orbital hybridization anymore in the CAPS syllabus. So actual fact that silicon oxide is actually not a linear molecule. It's actually a bent molecule. But for all intents and purposes, we're just going to handle it the way we would with the rules we have, which would mean that we have a linear molecule. So it would be the silicon bonded to its two oxygens, and it would make it a non-polar substance. And because it's a non-polar substance, we would say London forces. Then they ask us which one has the strongest intermolecular forces. Now, out of all of these that we did, the one with the strongest intermolecular forces is water, because water can form multiple hydrogen bonds. Okay, and it's just because of those multiple hydrogen bonds and because of the size of the water molecule that it is such a strong intermolecular force. The weakest one then out of all of them would be, of course, our noble gas, argon. Noble gases don't like bonding to other things to begin with, so, and then it bonds by means of the weakest intermolecular force. So that would be our weakest type of bond. Please test yourself on this. When I show the question in the beginning of the video, pause it there and see if you can do the same reasoning and get to the same type of intermolecular forces that I did. Also use that table that we did in the second video. It will assist you in actually finding these intermolecular forces.